Okay. So I'm going to talk to you today about searching for misdirected gamma ray bursts with a new telescope called the SkyMapper telescope. And so this is partially salesmanship on this new telescope, but it should be useful for anyone interested, especially in supernovae, but also in gamma ray bursts, because it will provide a nice digital map as SDSS is doing for at least part of the northern hemisphere. It'll do the entire southern hemisphere. So it's going to be located on top of Siding Spring, and it's a relatively modest telescope. And the reason...
We recorded.
Oh, sorry. Do I need to turn it on?
Yeah.
All right. So the SkyMapper telescope is a relatively modest 1.3 meter telescope, but it does not have a modest field of view. 8 square degrees at roughly 30 microns per arc second. So I'll show you. It's located at Siding Spring Observatory, which is the main observatory in Australia, especially since we burned down. And that was Mount Stromlo burned down. Our first light should be December 2006, so about 10 months from now. The telescope will be fully automated, and it's a replacement for the Great Melbourne Telescope, which conducted the Macho experiment, among other things, which is sort of the backbone of many of the Australian astronomers' PhD theses for the last 40 or 50 years. And at one point, this was the big telescope of the world in 1860, but it never worked very well. There's actually quite a failure, but by the time it got fixed in 1992, it was working pretty well. So this telescope is the same size as this, but instead of having a 40 arc minute field of view in 2 colors, it's going to have roughly more than 5 square degrees of imaging capability with CCDs. So why are we doing this? Well, there's no deep digital map of the southern sky and no instrument planned in the near future that can map the entire southern sky in multiple colors and multiple epochs. And in the same way that we in Australia are particularly into stellar astronomy, we're really handicapped by not being able to go out and have the interesting targets of, for example, very metal poor stars, very high redshift quasars, which are available in the northern hemisphere.
The VST doesn't do this?
It's an order, I'll show you, it's an order of magnitude smaller in its ability to do things. It goes much deeper, but it cannot do the broad coverage. The poor seeing, I will argue, and Xray has seen this before, and he would scream at me, but I will continue to argue this. The poor seeing for this type of science is a benefit. When you're trying to map out large pieces of sky in 0.6 arc second seeing, you need to have 0.2 arc second pixels. And when you have 0.2 arc second pixels, you don't have enough, you can't build that telescope yet. Pan-STARRS, another telescope, is trying to do that, but it's an order of magnitude more expensive. And so the reason VST has 0.2 arc second pixels is because they have 0.6 arc second seeing, but they can only do a degree at a time, and where we can do 5 times that rate. And so now, because we're technology limited, and you do not, for photometric purposes, want to undersample your images, you really are at an advantage with the poor seeing. Given technology in the future, hey, but this is an experiment. I want to do what I want to do. This is an advantage. Pardon? And for us, the science capabilities are broadly relevant to Australian astronomy. We're matched to the capabilities of a new instrument, AAO Omega, 392 fiber, 2 degree field instrument on the 4 meter Anglo-Australian telescope, which is just being commissioned now, that has about 20% throughput. So that would be a very nice instrument. And of course, it's a natural replacement to sell to government, which unfortunately hasn't worked terribly well, of the destroyed 1.3 meter Great Melbourne Telescope. So this is Siding Spring Observatory on a nice, clear photometric night, as it always is up there. It's not as good a site as the other southern observatories, but it's a useful site, and it's cheap to build at relatively, and it's easily accessible, etc. So the telescope itself looks like a little lollipop. It's going to be extremely small, 6 meters across, the whole thing, which sounds bigger than it appears, 11 meters tall, a very compact f1.2 telescope, so it sort of looks like a giant suitcase when it's done. It will not be impressive to look at. But small telescopes hopefully will provide nice seeing. And so this is pre-built off-site and then comes up and it's just sort of assembled on-site, and that'll be happening in the next few months. We have the ability to move these apertures around to help reduce wind, shake, and things, which should be useful.
So just the vent doors there are to improve the seeing, right?
The vent doors are being so that you can move air through if you want. It's not so much to improve seeing, it's to make sure that you get the most out of the site. Because I know that sounds like a joke to you, but if you go to most of the 1 meter telescopes in the world, this size telescopes, they all get 2 arc-second seeing. If you go to the Swope 40-inch at Carnegie, which is a great seeing site, it gets 1.8 arc-second seeing, even though the site's producing 0.5. So the reason, one of the big things about the 8 meters is they get half arc-second seeing when there's half arc-second seeing. And that sounds, oh, it's easy. And indeed, I can go to all sorts of telescopes. The Arc 3.5 meter does not deliver the seeing at the site. Wind does, but it's easy to make mistakes on this. So it is important. I think it's very easy to take for granted that you can get great seeing now on telescopes, and it's not. People have spent lots of money to do it. And for a little telescope, you take shortcuts, you're going to end up with 2 arc-second seeing, just like you did in 1960. So this SkyMapper telescope is being built by Electro-Optic Systems. Electro-Optic Systems is based in Queanbeyan, which is very much where I live, and Tucson. They have built the Sidekeck telescopes, which have recently been canceled. So I think they're sitting around with 4 1.8 meters hanging around with no home right now. But it's very useful to have your telescope manufacturers, who I think most people will understand have built a telescope. Telescope manufacturers, you always have a hard relationship with them because there's always problems. And the ability to have the people building the telescope, 3 miles down the road is very useful, because I can go down there and bang on the door and make things happen. So it's quite useful for us. And the design of the telescope is what I'd call a modified Cassegrain. You have let me lead you through this. You have a 1.35 meter hyperbolic primary. It's basically a Ritchie-Chrétien, for those in the know, type of surface. Comes up to a very significant 0.71 meter secondary, which again is a conic section, a hyperbola. And then it comes through a complicated piece of optic, a 0.54 meter fused silica A-sphere. So why are we using fused silica? Because fused silica transmits UV to IR 98%. You actually lose more on the reflections than the internal stuff. It's expensive, it's hard to manufacture, but Sagem can do these things now if you pay them lots of money, which we are. So this is the big complicated piece of glass in the thing. It's not horrible, but it is the one piece of glass. It's hard. And then you have a bunch of fused silica spherics again. So the whole optical system is reflection and fused silica. We'll be using a protected aluminum here on this surface and on this surface on top. Why? Because we want ultraviolet throughput on this telescope. And although aluminum has very good throughput in the ultraviolet, it oxidizes in a couple weeks. And so your UV throughput off a mirror, an aluminum mirror, if it's not protected, drops dramatically in the first couple weeks. So it looks really good when you get it, and then you still can't see it with your eye, but it doesn't transmit well. The other nice thing about protected surfaces, you don't have to re-illuminize very often. All right, the imager we're building in-house. It's a 268 million pixel CCD, so very similar to Omega Cam on the VST. It's 32 E2V CCDs, which are arriving. We've got about half of them now. $2.5 million Australian worth of silicon. The nice thing about these CCDs, and these are deep depleted, broadband coated. So they're deep depleted 40 micron devices. That gives you less fringing and better IR throughput. Broadband coating means you still have pretty good UV, so they're typically 60% at 300 nanometers throughput, and about 60% at 880 nanometers. So they're very broad throughput. That's useful to be able to do anything you want with the things. And cosmetically, they're the best CCDs I've ever seen in my life. The first CCDs we've gotten have had typically 50 bad pixels out of 8 million each. And those are so just absolutely clean devices. Very low read noise. We're getting 2 electrons read noise slow. We're going to be reading them out very, very fast through Pan-STARRS readout electronics, which are these beautiful new boards that Peter Anaka and John Tonry are developing as part of the Pan-STARRS project up in Hawaii. They are working now. We don't have them, but they're working in Hawaii. They'll be shipped in the next couple months. And with these things, we can read out one of these CCDs through a single channel, so 8 megapixels, at about 10 to 15 seconds, depending on the read noise we want. And so we'll probably choose a readout time. Well, we're going to see what we actually get through it, but it'll be between 10 and 15 seconds to read out 8 megapixels. And the read noise should be between 4 and 7 electrons, depending on exactly what happens. So that's quite remarkable. And since we're sky limited, the read noise at that level is only going to hurt you in the U band. And if at 5 electrons, it doesn't even really hurt you in the U band. All right. We have a 6-filter slot. One of the problems about this instrument is this instrument has the same scale as the telescope, right? I mean, the silicon is this big, and the telescope's that big across. And so trying to get this to fit on a little telescope is quite a challenge. And so we have filter slots, as I'll show you in the next slide. We have 6 of them, which are up above things. We've made sure there's no ghosting and reflections that have plagued things like the 2.2 meter at ESO, where they unfortunately had this nice optical collecting thing that takes the skylight and sort of reflects it back off on one thing onto the CCD and makes it almost impossible to flat field. It's no liquid nitrogen. Everything's done with helium closed cycle coolers, and it has a Shack-Hartman built in so that you can collimate and focus whenever you want just using a Shack-Hartman system. All right, so here is the throughput of this telescope to a limiting magnitude. And so obviously VST, if you want to go faint, 24th magnitude, it's an order of magnitude better than this telescope because it has much better seeing. It's a much larger telescope. But it does observe 5 times less sky, and it has a longer readout time by a factor of 3. So if you want to do things quick to 20th magnitude, SkyMapper is an order of magnitude faster than VST. Furthermore, it's a dedicated telescope. VST is split across the European consortium, and there are some big programs, but those big programs are not 75 or 90% of the telescope. They're 10 or 15% of the telescope. And so we can do different types of work. And indeed, we're going to be complementary with these things. I'm slowly convincing them that they need to use our calibrations of the sky rather than doing all that themselves. So this is a mapper of the sky. So the main thing that this telescope will do will be to provide a survey of the southern sky. Multicolor, so 6 colors, I'll talk about those in a second. Multi-epoch, 6 epochs, every piece of the sky in each filter. So we want to get variability and photometric information. We will do the whole 2 pi steradians below 0. We are setting our benchmark of 3% global accuracy. We actually expect to do better than that, but that's what I'm stating I will do. Our astrometry would be better than 50 milliarc seconds. We'll probably do better than that as well, but again, that's our stated benchmark. And we will, in our variability, undertake those separations of each part of the sky on scales of hours, days, months, and years. Why? Well, there are things that move and change on scale of hours. For example, Kuiper belt objects, they move on scales of hours. And if you come back a month later, then you can't tell what's going on. RLIRE stars change on hours. On days, you have things like, cataclysmic variables sometimes pop up. You have other variable stars, Cepheids. You have a whole range of things. Months are things like supernovae and other variable stars. And years, quasars, Mira variables, all this gambit. And so by having that extra information of variability and the very good color information we have, you'll be able to sort of figure out what literally every object is in the sky, at least better than we can now. The data will be supplied to the community without proprietary period. You don't need to buy in, sign your life away. It is not. I am not doing, and intentionally not doing, the SDSS model, because I just don't think it's the right way to do things, at least from my perspective. And it does mean there are shortcuts we have to take because we don't have the money that SDSS has, but we're doing things in a different way, and I want to bring the community in and make this a success by basically doing my best job, but then making the data available to the wider community so that everyone can use it. And I figure that's the way to actually make the program the biggest success from our perspective. All right, so here's our filter set. It's very much like a Sloan filter set, except for there's two differences. One, our U filter. Our U filter is a stellar-friendly Stromgren U. Right? It has very little flux above the Balmer jump. Why? Well, if you want to figure out a star's gravity, okay, that is sensitive between the Balmer jump. And so by having your U filter down below that, you can really figure out the gravity of a star very well. The other thing we've added is a Stromgren V. It's not quite a Stromgren V. It's something we've optimized. It comes up right at the Balmer jump and then gives you the first 300 angstroms from about 3,800 to 4,100. And that's very sensitive to metallicity. It's also sensitive to gravity, but because you have this filter, you can break that degeneracy. We have more or less a G filter, which is like a Sloan G, an R and I, which will also be like Sloan R and I, and a Z filter, which is similar. Now, relative to the Sloan filter, our system has better U throughput than Sloan, a lot better Z throughput than Sloan. And so despite being a telescope that's 1.3 meters, so we're a factor of 4 down on SDSS in aperture, we're integrating. We have basically, in these filters, more than twice the efficiency, but then we're also integrating many, many times longer than Sloan. So in the end, our ability to reach limits in a single 90-second image are very similar to Sloan. But in a 540-second combined, so the 6-image combo, we're actually going deeper in Sloan than every filter. So the whole system, the combined photometry, will go a little bit deeper than Sloan. Now, truth be said, the little bit deeper in Sloan is not that interesting because what you're going to be working on there are galaxies, and galaxies, the VST is going to do much, much better.
Right. 6 epochs over how long a period of time?
Well, it'll be over 5 years, the whole survey, but we're going to basically release the data when we have groups of 3. So the whole we've done, when we have 3 observations in every color, the data will be released, and then we'll do the next 6. So the whole sky will be done in 3 epochs within a couple of years. But the data will be released as we accumulate it. So how does this work? We have 3,200 hours of astronomical time per year. 40% is unusable due to clouds. Now, we do take a hit relative to northern Chile. It turns out relative to southern Chile, what they don't tell you in southern Chile is it's perfectly clear this time of year in Chile. But during the winter, we actually have a higher fraction of useful time in Australia than they do in southern Chile. And that's when the nights are really long. So the total number of useful hours in Australia is surprisingly close to a site like Cerro. Now, our seeing isn't as good, but it's not as bad as you might realize. By definition, we are defining the survey to use the best 2/3 of the seeing. Now, our median seeing should be about 1.5 arc seconds. That has to be delivered. The DIMS sort of come in at 1.1. The AAT has 1.5 arc second median. So we expect to be able to achieve that, but our current telescopes certainly do not, but they're the old school. And so this 1/3 data, which is too poor of seeing to be used for the survey, because you want the survey to be nice and homogeneous, is sort of orphan time. Within this, we'll be doing, as I said, these 6 colors, 6 epochs, which is roughly 4,800 hours of telescope time. And we're going to make this last for 5 years. Again, tuning things to last for 5 years. We'll also be doing a 5-second survey of the entire sky, 3 epochs, and that's to photometric calibrate the entire sky to roughly 16th magnitude in all of our filters. That will be made available almost immediately. So in the future, if you're below 0 declination, you go out and you look, you'll have a 16th magnitude star every couple arc minutes, which you can calibrate your data on. You will not need to take standards anymore. And that will be the first thing we do. Okay? So we estimate there'll be about 570 hours a year of poor seeing but clear conditions. If we do 35 seconds per pointing, that's 20 seconds on sky and 15 seconds reading out, gives us 58,000 pointings a year, 5.1 a hit. That's 300,000 square degrees of monitoring we can do a year. That's a lot of monitoring. So this is an order of magnitude more than what people are doing now. Basically, that's 5,750 square degrees per week we can do a supernova search with, where you just use the bad seeing and you go through the sky. And 5,750 is, that's sort of the sky that you can see during a night. That's the easily observed part of the sky every night. So our poor seeing, as in searching, I've done a simple Monte Carlo calculation where I've assumed that the data we get is uncorrelated. I haven't put weather correlations in there, but I think it's pretty close to being uncorrelated when you put the seeing in. It includes the effects of the moon, night length. The observations are G-band observations with 20 seconds and a 15-second dead time. We'll imagine that when we subtract the data, we're going to ignore anything fainter than 19th magnitude, even though we have signal fainter objects than that. And the reason we do that is things get hard between 19th and 20th. That is, you get junk, you get asteroids which are uncatalogued, all sorts of things. We assume that the average seeing of this time will be 3.5 arc seconds. Most of it, my guess, will be at 2.5, but there'll be some at 4 and 5. So it's a reasonable average. Basically, the signal to noise we get at 19th magnitude in dark conditions will be 17, 13 in gray conditions, and at full moon we only have 5 at 19, so obviously you're not going to go that faint. You have a signal noise at 10 at about 18.2, and that's only for this couple days right around bright time.
And that's just in the G-band?
That's in the G-band.
You'll have information from the other filters?
Eventually, yes. So what do we find? Well, here's our Type 1A survey detection in a 5-year program. Basically, as a function of redshift, you obviously peak as you go to the edge of your survey. But you can imagine at 0.08 finding roughly 500 objects to a redshift of 0.08. Why 0.08? 0.08 is a useful redshift because the objects are still bright enough to follow on moderate-sized telescopes. They're easy. Where when you go to 0.1, they start becoming very difficult as they fade away. So for the purposes of a gamma ray burst experiment, these are the things you need to get rid of. Just to show you the other things you'll find, 1BCs, making some rough guesstimates about how bright these things really are and their distribution, which is not terribly well known. You'll find a lower redshift group of them, but some extending to high redshift because of their intrinsic dispersion. And type 2s are very similar. And then there are, as Peter said, the things I have not included in this simulation are these very bright 2N things, which are very rare, but when you do pick up at a redshift of 0.15 or 0.2 when you do these experiments. All right, so let's say I want to go out and find misdirected gamma ray bursts. Why would I want to do this? Well, I'm very interested in the supernova gamma ray burst connection, and in the last 2 years there has been exactly one object found at low enough redshift to be studied, and of course it's the one we're dealing with right now, and it's a wacko object which is not obviously related to the normal gamma ray burst we study, although it is of the same ilk. And so if we're going to really understand these things in the future, we need to have a larger sample. And if you wait for the gamma ray burst to go off, well, Swift's going to be dead and buried long before we have built up a sample of more than a couple of these things. And so the idea here is to go out and find the objects which are gamma ray bursts, which are pointing in the wrong direction. So bright Batsy bursts have a rate of about 2 per gigaparsec per year, which translates to 1 per 10 to the 7 per Milky Way galaxy per year. But they're beamed. Now the beaming fraction is quasi-unknown. There are certainly some probably correlations with various other parameters, but I think most people would say they're beamed by a factor of 50 to 500, with a good guess being an average around 300. you can choose your own value. And so that means that this value here, you only get maybe one object within a volume of 0.1, z of 0.1 per year. If you get to multiply it by a factor of 300, you have 300 objects within that volume. And so suddenly, something that is essentially impossible to find, a gamma ray burst, a nearby one, becomes relatively easy because there's so many of them, if you can cover a big fraction of the sky. And of course, our supernova program is going to cover a big fraction of the sky. So, I also mentioned that there's obviously must be a fainter, more common subset of objects than these 1998 than the normal ones, these 1998 BWS ones. Now, which we know two, which are at low redshift. We don't know how many of these things are, but there certainly are more of them than there are normal gamma ray bursts, given the fact we have two in such a small volume. They're not very bright in gamma rays, and it's not even clear that we'll be able to figure out that there are gamma ray bursts in all cases using our techniques that you can look at them afterwards. But there are more gamma ray bursts than this normal number that I'm going. So if we do a Monte Carlo simulation for these, I'm just going to assume they have an absolute magnitude of minus 19 plus or minus a half. There are objects like 2002 AP, which may or may not be, in some cases, a GRB progenitor. Those are fainter than minus 19. And there may actually be more of these that are fainter than I have listed here. I don't know, but this is a reasonable first guess. So, what about the number of broadline 1Cs, aka hypernovae? Well, this is a very funny number to estimate. Philip Podsolowski has attempted to do it. I'm just going to go through and do it from scratch in a similar analogous way, which is to compare the number of these things discovered relative to the number of type 1As discovered. Alex Filipenko and other people have been very consistently finding objects since 1997 to a redshift of about 10,000 kilometers per second. I won't say they've discovered all of them, but I would say that when they look at a galaxy, they find the type 1As in those galaxies. And since hypernovae are more or less the same brightness, right, I'm going to do a relative rate to the type 1As. Okay? Now, hypernovae are a little fainter than type 1As, and they've got dust. So again, I'm going to be underestimating the rate of hypernovae probably, but it's going to be close.
Brian?
Yes?
Shri is not here, but just a few days before, or whenever he gave a talk, and he insisted that we remember that hypernovae are not the really bright things that everybody makes it out to be, but there's a big distribution.
As I have said, I think I've just covered that I don't know what a hypernovae is. I'm talking about broadline 1Cs. And as I said, a lot of them are bright, but there are a few faint ones. I agree. There may be a lot of faint ones. Okay? And so I'm saying this is a lower estimate. There will be at least this many. There may be more if there is a lot of faint ones. Okay? And I think I mentioned this in this part here. There's some caveats to what I'm doing. But I can't do anything better because there's just not any information out there. All right?
Sorry, Brian. However, the number of hypernovae today is about 10.
Yeah. I mean, I think it's a matter of terminology. In fact,
broadline 1Cs to below a redshift of 0.033 since 1997. I think there's 5. Yeah. There's actually 7 now, but 2 of them were discovered by gamma rays. I'm not including them because they weren't discovered by the optical. Okay? And I think there's only 5.
Up to 6,000 kilometers per second there are 8. I have at least.
Give me your number. I'm curious what we have. I mean, I went through it and I think there's.
97EF.
I'll tell you now.
Yep. You exclude 98EW, okay? Then 2002 AP.
Yep.
2003 JD.
Yep.
2004 AW.
Yep.
2002.
2003 JD.
Yeah, we've already said that. Okay. We agree on them. We're within 1.
2004 BU.
Yeah.
2003 LW.
No, but some of those. No, 2003 LW. What's the redshift to that?
5,500.
It's full of hydrogen and things.
I told you.
No.
Below 6,000 kilometers.
No, but it's not what I call a broadline 1C.
Yes,
there's hydrogen in it.
Well, one of the ones he's listing. We can go through the numbers.
But there's a broadline.
This is a lower limit. Pardon?
It's right.
Is it a broad line? Is there a broad line too?
There are different values of what copper. I'm happy to argue about the number. I get a plus or minus square root of 5 right here on the Poisson limit. Okay? I'm just trying to get the basic numbers to scale up. Okay?
Wait, but I just want to make sure when you say, are there any broad line objects that are not onesies?
There is certainly one that is what is described as a hydrogen-rich hypernovae, which looks funny, and I have certainly excluded that, and it is one of the ones he referred to is in that list. I excluded that one. I'm just trying to get the order of magnitude here to see what I'm up against.
Yeah, I'm just.
Right?
I mean, if there is a broad line thing with hydrogen in it, that's actually more interesting than any more new 1Cs you can find. That tells us. I mean, if you want to constrain the mechanism, if you say if you get a broad line, so I don't want those thrown out of the sample. I was working on the theoretical engine format that I needed to get. I needed something that made it a 1C, made it broad line.
Yeah.
If there's a broad line object that has hydrogen on that tells us, I might as well throw away a lot of the models.
Well, I think.
What is okay? It's a 1B.
It's a 1B.
1B with a little hydrogen.
Okay. It's just it's a 1B with a little hydrogen. Okay.
Yeah. Okay. Well, let's go through that. I can't remember these things off the top of my head. I'm sorry. So, if I scale to the supernova rate, these things have a rate 55 to 1. It may be 30 to 1. It's not 10 to 1.
Yes. Please go to the bottom line. What is the percentage of so-called hypernovae out of total number 1BC?
Oh, I don't care. I don't know the 1BC rate very well, so I'm not going to go there. I'm going off the 1A rate. I'm saying they're roughly 50 times less frequent than a 1A. Okay? It's an approximate rate. It's a lower limit. It's a lower limit because hypernovae occur in little dinky galaxies, and Kate doesn't even look at those in the nearby universe. So there's going to be a bunch missing there.
Yes, that's 1 in 100 of the core collapse rate, so that's okay.
Yeah. It's on the order. Yeah. Okay? So also Kate looks at elliptical galaxies, and so their rate is skewed to extra 1As there, etc., etc. So my guess is you probably can knock this down to maybe 20 to 1, 30 to 1, something like that. Okay. Again, we're going to assume for consistency with the previous calculation they have an MV minus 19. Now we've already said we know there are ones that are fainter than that. These are the bright hypernovae. Okay?
Ron?
Yes?
Another question. When you're doing this search, how much of the galaxy are you going to look through to do this search? I mean, are you doing your supernova part away from the galactic plane?
There's no sense going through the galactic plane.
I was just wondering if you have a choice in that matter.
Yeah, 6,000 square degrees is a nice amount because you always can see that amount of clear sky without going through the galaxy. If you go to, you've got about 13,000 square degrees, which are above, 30 degrees out of the galactic plane, and so that's enough. All right, so here's the hypernova extrapolation at 55, 1/55th of the 1A rate. Here's the GRB extrapolation that if you just take a beaming factor of 300. So what you notice here is they're broadly the same order of magnitude, within a factor of 3. I mean, this two numbers are a factor of 3. Now, we've already determined, we know that the GRB rate is probably low, and we know that this is low. But they're within a factor of 5 or 10. It's not 100 to 1. It's on order of 5 or 10. So every broad-line object we look at, you probably, this would say you probably have a 1 in 3, 4, 5 chance of it actually being a misdirected gamma ray burst, just to match up their rates. This is the only point. It's not precision. I'm just trying to do...
It's okay. I mean,
yeah.
Between 10% and 25%.
So Alicia, I'm sure, showed this plot, which unfortunately I made her make as her referee for her paper, despite being in the acknowledgments, which was an interesting... Never had to referee a paper I was acknowledged in. Anyway, the calculation that you can do by looking at late-time radio objects of these bright lines gives you a consistent answer right now. Basically, with 84% confidence level, she can say no hypernova, no nearby observed hypernovae is a gamma ray burst. Okay? But, 50-50 is sort of, half of them or a third of them, she doesn't have constraints on that yet. So it's consistent with the radio. So we want to separate the wheat from the chaff. That is, how am I going to nail the fact that I have hypernovae? Because I've got all these type 1As I got to deal with. There's huge numbers of objects. So each night's data will be subtracted with new candidates photometered in G. All right, and I'm hoping Peter Nugent, who's got lots of experience, and his group at LBL can help in this because it's a huge job. Each candidate will be confirmed at subsequent nights observing in VGRI. So what we do is we find an object, and then when we think we have a reasonable candidate, the next night we will observe it in VGRI. So that gives you two things. Removes any surprise asteroids, because the asteroids are well cataloged down to 19, but they're not 100%. And so asteroid will have moved in 24 hours. It shows if the supernova is on the rise, decline, or flat. So if the object is on the rise, which I'll show you most of them will be, you'll see that. And that helps you discern what it is. But finally, it provides very good chance to do color discrimination on the types of supernovae. So here is what a type 1A distribution will be as a function of redshift. This is the time, the age that we expect. Minus 20 days, plus 10 days. And so obviously the nearby ones you find early, and as you go out here, you get a scatter. If I restrict myself to redshift less than 0.08, this is the average days, about minus 8, minus 9 days, with a reasonable distribution. So how am I going to do color discrimination? Well, here at roughly a little bit before maximum light are the distribution of three major subtypes of supernovae, the broad scale distribution. So this is 98BW, this is 2002BA, this is a type 1A. Now if you look, there's some differences if you have broadband photometry here. Note that the type 1A is faint in the IR. Note that the hypernovae is very bright here, faint here, relative to the supernova, which has got a nice thermal spectrum. And so if you look at the SkyMapper Filter Set here, you can see that by comparing here and here, the V, Stromgren VG, you're going to see a difference. You're going to separate these things out a bit. These two, you'll separate these out very nicely, separate these out a bit. But then when you go to the GI, for example, or the RI, as I'll show you, then you can separate these things, the type 1A, and this is going to separate out. So that's just the idea of how this will work. Using Peter Nugent's templates, which are extremely useful if you have them, I plot the curves of these objects when they're within 1.5 magnitudes of maximum light, when you're going to be observing them. Here's a type 1A curve. This is right at explosion. They kind of wander over here. This is the 1BCs and the 2s, which are pretty much impossible to discriminate in this color set. They just sort of lie on top of each other. And you have hypernovae, which are nice and separated. Now you could say, well, what about extinction? Well, I'm trying to separate the wheat from the chaff. I'm actually trying to separate the chaff from the wheat. These are the chaff. The wheat, the stuff which the bulk is, are up here. These are the things, when they have extinction, go up this way. They don't go down into your hypernovae area. That's useful. The hypernovae, if they're extinguished, will disappear. But most of the hypernovae that we're interested in, or what I'm expecting to see, of course, are going to have moderate amounts of extinction. That is what they're going to look like what we see already. And so these objects, most of which you will see, you'll still be able to discern them. The type 1As go up here, but you have to have a lot of extinction on a 1A, and we will make mistakes due to that. If I restrict things to rise to just after maximum light, so this is where about 85% of our objects are discovered. You can see that they're on the rise, or they're within a couple tenths of a magnitude of maximum light. And then the separation is much, much cleaner. Type 1A is way over here, hypernovae in a very small little space here, and the 1BC is still causing you a problem. Of course, we can observe in U and in Z, and it turns out you can start separating these things if you want to do that in those filters.
So how many objects are you going to keep following though? I mean, after you find something? Are you going to follow all the supernovae?
Well, we're going to try to follow everything less than 0.08 that we find interesting. So we will attempt to get a typing spectrum of all the objects, a single spectrum, and then we'll decide if it's a type 1A, and for example, the LBL guys want to get a spectrophotometric sequence of it, fine. We can do that. I may just want to get a redshift and then get a light curve of it. This is taking care of over 5 years, so we have a lot of telescope time. So
let's one telescope. How many false positives do you expect, and how much time do you spend to keep on following instead of rather than mapping the sky?
Very small, less than 1% of the time.
False positives. We do 5,000 square degrees in a week and a half, 2 weeks, and
but besides
things that actually go to be followed up that aren't a supernova,
that's what I mean.
1 out of that entire week.
You have to say, well, what's going to suddenly appear as a star over 2 days and have a color that looks like a supernova, and it's come out of nothing? The answer is cataclysmic variables, occasional flare stars, but of course you get rid of those because they're very red, and you can pick these things out and see that they're weird. And there will be a little bit, but there's not much, as long as you take multiple observations.
We've taken spectra of 3 CVs out of 150 from the supernova and 2 AGN, and we had a much, much cruder thing than what Ryan's talking about. So that's a really small contamination.
And the CVs look like type 2s. Right? They're just this big hot thermal spectrum. They look just like a type 2. And, if you want to go after, Peter's interested in following type 2s, and there will be some problems. But all you have to do on those is say, type 2, let's wait a couple days and see what it does. And if it, it's going to either follow a type 2 like her shape or it's not, because the CVs and the type 2s will be different.
It's all automated, right? So are you planning to send out trigger this thing that you find something?
It will be automated, but every morning the monkeys will be in there going, looks good, looks good, looks good. You got to have that. Yeah. So how are we going to figure out once we find these things if it's really a misdirected gamma ray burst? Well, there's 2 ways you can do this. The primary way is Alicia Soderberg's method, which is you just follow them up in the radio. And we have access to the Australia Telescope Compact Array, which provides you about the same sensitivity as the VLA. It just has to synthesize for 12 hours. But its limiting sensitivity is about the same as the VLA, because although it's much smaller in a real size, the electronics are much better than the VLA. Now, when the VLA gets upgraded, it'll start catching up, although we're getting a big broadband correlator, which will give us an advantage. So we can get down to quite sensitive limits. And the idea is that if a jet is misdirected, it expands, and eventually you will see the radiation come towards you after several hundred days. And this is from Alicia's recent paper, where she just models various angles of where the jet could be. If it's a gamma ray burst style jet or a 98 BW style jet, you're fine. And as you can see, at any reasonable redshift, for example, redshift to 2003 JD, you can find and get good constraints on these things. The other way for the impatient is possibly, and I can't figure out quite the sensitivity, is that dust around the GRB in the host galaxy of the hypernova can scatter the gamma rays and X-rays, and it is possible that you will be able to see the reflected light with a follow-up with Chandra, analogous to this reflected light on a gamma ray burst in GRB 0312. Yep. But in this case, the dust was in the Milky Way. All right? That's not what we want. You need to actually have the dust in the host galaxy where it would be reflected and scattered. And I've seen a calculation somewhere which I could not find on AstroPH in my life where this is a reasonable way to also maybe pick these up. And the advantage of this is you can do it instantly, where this you have to wait several months. But those are your 2 ways that I know of following up. And at this point you will have a beautiful optical, spectral, and then with the radio you can imagine getting a reasonable handle on the energetics especially. This sort of tells you how much energy is in the jet, and study the connection in, how do I say, a more, under more cases than we're going to get otherwise. So our software philosophy is keep it simple. This is in a $12 million Australian project. It's about $9 million US. And that includes the telescope, the camera, the postdocs, the software, and the salaries. So compare this to Sloan, which is $100 million. 2MASS spent $27 million on their software alone. So we have to keep it simple. And it's not that you can't keep it simple, but you just cannot. When people say, I'd like to have this feature, you just say no. No. No, we're not going to write that piece of software. Yes, we are going to use source extractor to find objects. We're not going to rewrite that. You just use everything. So we're keeping it simple, keeping things low risk. We're reusing essentially everything.
That's a 5-year cost?
Yes. Things are cheaper in Australia.
What about the software for distributing things, or that you're just going to put it somewhere for distributing all the data?
The data will just be a URL that you go to. Keep it simple. If you go to 2MASS and try to get data out of 2MASS, pull my nails off my fingers by the time I'm done with it. Way too complicated. It's a little thing, RA-DEC, click it, and it'll give it to you. Keep it simple.
Sloan's just as bad. You have to go and put in, fields and things like that.
Yeah. No, it's going to be simple. RA-DEC, I can tell you what it'll be, but it'll be something which I like, which means RA-DEC simple. And I'll probably write a little Perl thing you can put in, and it'll just automatically grab it for you. You can, hit it. And it's being, as I say, this is all being done. One of the things that I'm not including in the cost, which I have for free, is the supercomputer, which is the Australian supercomputer, which 1800 processor system just came up, Vitanium 2s. It's a very nice computer. I think it's number 19 in the world or something right now. And I can just sort of run stuff on this when I need to, and it turns out that will chew through the data very quickly. I need less than 1% of it to do what we need. Attached to this is an equally useful petabyte storage array, which is a disk farm system, high-speed disk, with about 50 terabytes of cache. And so what you do is you just give it a list of the files you need, and it starts getting them in order, but it optimizes so it does it. And so by the time you're done with your first one, it has the next 5 or 6, and it's a very efficient system, which I've used for the Macho work that we've done. And anyway, it works nice, and they take care of it. We flat field the data in world coordinate system just immediately. We difference to an earlier reference. We reference everything to the 5-second survey data. And then our spectral follow-up will be with the 2.3 meter in WIFES, which is a new integral field spectrograph, which we're putting on that has a end-to-end throughput of about 30%. It's very similar to the SNF spectrograph, except for this has got an image slicer and VPH grading. So in theory, it should be slightly higher throughput. And that's just sort of a point and shoot. And it turns out it gives you amazing ability to get spectra of things, even in 2 arc-second seeing to 19th magnitude. It's a very effective way of getting your redshifts. And I can easily get 50 to 100 nights a year on that instrument. So our concluding timeline. Well, this funding decision was 2004. We ordered optical elements then. We've had our our conceptual design review, ordered our CCDs, had our critical design review. We've had a bunch of mirror blank failures, which...
Everybody has.
Oh, this was terrible, anyway, which I'll go through in just a second. Our site works have begun. First light's still scheduled despite the mirror blank failures in 2006. Regular operations probably about April 2007. And so this is our cracked mirror blank. We had 4 of these crack. So there's 4 dead mirrors. And we are now going a more traditional method to get a solid blank made in Russia, who seem to always deliver things on time and on budget. And they're supposedly going to be delivering the mirror in about August, I believe. And as near as we can tell, they're on schedule to do that. All right, we'll stop there.
So one of my issues with surveys is there's a lot of photography going on. How much, and you probably mentioned it, but how much do you have a lot of stuff developed to do spectral studies of any of these objects? Are you going to, how much can we expect for spectra of objects? And how much spectra? One spectra per supernova, or can you get several?
Well, for the interesting objects, we can get several, and I'm talking to Saul and company about they're very interested in getting sequences on every object, which requires lots of time. And while that's one thing to do, it's maybe not something you want to do on 600 or 700 objects. You may have to choose a subset of them to match the available time. But it depends on what you're trying to do again. So, doing 100 objects with 10 spectra, not a problem. Doing 500 is pushing the edge of what we can do. But, the interesting, the hypernovae, trust me, we'll get lots of good spectra of those. But every type 2 that goes off, probably not. At some point,
Yeah, I go back to my comment of, if you find something that's not a 1B, 1C that has broad lines, so a type 2 that has broad lines, that would do more to change the theory than any other observation you can get. But if you're not taking spectra of any of your type 2s, would you ever know?
I'm
sure it would change the light curve too, but the issue is, are we going to miss something that would be the best constraint of the progenitor, say?
It is possible. Clearly, one of the things that you'll be looking for are the unusual objects. Okay? And so there's at least, in my thesis, there was a very bright 2P, which was, minus 18.6 absolute magnitude on the plateau. And, it's pretty hard, no matter what you do inside of a big 20 solar mass of hydrogen envelope, to make anything other than a 2P, right? You're not going to give it broad lines. This had broad lines, but they were 10,000 kilometers per second. But it was incredibly bright.
Which one?
1992 AM. I think it's the brightest 2P still.
The brightness P depends on energy and kinetic energy of explosion and radius. So nothing nickel mass. That's important.
Depends a bit on nickel mass.
If it's a battery, it's based on nickel mass.
And this one, I would argue, probably had, although the observations aren't very good, had a lot of nickel as well. Like 3 or 4 tenths of a solar mass of nickel would be the best guess. And it was incredibly bright on the plateau. But, there's one of those known. And if something like that occurs into a galaxy whose redshift we know, and we know it's a type 2 that's doing on the plateau, we'll immediately take, we'll say, oh, bright type 2 on the plateau, what's going on here? But the problem is you're going to be hit by these 2 ends, which are going to be very difficult to discern. That's why a single spectrum would be useful.
Can you tell us a little bit, so I'm just trying to be sure I'm keeping track of it. So during bad seeing, you do a completely different cadence.
Bad seeing will just be, essentially, the mode I have is do the entire visible sky in the night, or whatever you can. So you're just going to cycle through, you're going to cycle through all these fields which are visible to the supernovae, and essentially you'll have a list of active things, and then, if the bad seeing is one night and then the next night, well, you're just going to try to essentially go through your active list.
Because what I'm trying to understand is if I just think about the phase space, if I imagine a transient that has a time scale of an hour.
Yeah.
Okay. Where does that get caught in this with this?
It gets caught as a thing that came up and the next day is gone.
So there's no cadence of an hour return time?
There will be the cadence would be 3 or 4 hours. In the main survey, there'll be stuff with the same night.
Okay.
And there will be things that pop up, and typically you'll probably have 6-color photometry on it, because we're going to try to make all the photometry at the same time. Then you come back 3 hours later, you take another picture, you'd see object gone, no asteroid nearby, and the problem is, if the asteroid's moving fast, you'll actually see it in the 6 images move. So you'll be able to pick these things out. It's not going to be easy, but it will certainly, the information is there to do that. to have things that pop up and disappear. The problem is you got 6-color photometry on something that like that.
Yeah.
And of course, it probably is changing rapidly in those 6 colors.
Sure.
So it's going to be, you'll know they're there, but they're very hard to deal with.
And there's a few funny objects that were found in this paper by Becker from the Deep Lensing Survey.
Yeah. So
A few of these funny
well, because we found them in the High Z search as well, and that's sort of got Andy doing it the right way.
Okay.
And yeah, a lot of them look like flare stars in the Milky Way. That is, there's at least half of them look like.
But then some of them had no deep counterparts in the end.
Well, they're really tough to see.
Star or something.
Yeah, but then there are a few where there's one that happened in a galaxy. So that one I certainly accept. And a shock breakout of a supernova, maybe. Who knows?
Brian, I assume no guiding?
No guiding.
Okay. And so the 6 filters are, how are you doing the colors? You're doing one right after the other? Okay.
Yeah. As best we can.
So with the readout and everything, you'll have sort of a temporal coverage of a couple minutes or so. Not even a minute.
Well, it should be 35 seconds end to end.
For all 6 colors?
No. I mean, it'll be.
Per color.
Yeah, it's 35 seconds per color.
So it's times 6. Okay. So 3 minutes total coverage.
Well, that would be the fast mode. Yeah.
Right. No, I'm just saying.
For the survey, it would be more like 7 or 8 minutes.
So you can discover things that will temporarily evolve over 3 minutes.
Yeah.
In each of the filters.
The difficulty will be, you're trying to use that for your spectral information, and of course the object is changing in some unknown way.
No. But shock breakouts, I mean, you're in the gene's tail, so you have a very good assumption of.
If you know it's a shock breakout.
Right. Well, I'm just saying that would be the most interesting case of finding something on a galaxy that you can clearly see, and you have something that follows the gene's tail and it's just changing rapidly.
Yep.
And it's a trivial model to do.
Well, I think Roger would disagree that it's a trivial model.
Well, the trivial models are fine.
But your software to do all this is written up, or you're just going to?
No, it's being worked on now. So, I mean, well, as I said, a lot of the stuff is being reused, but it's just gluing it all together that's hard. So, yes, we have big work packages and little tickets which I have to tick off.
I mean, I thought your estimate of the amount is for computers and storage space, but I guess you said you can mostly use a supercomputer for all that.
I can use the. I mean, it's a $25 million thing that I don't have to pay for, which I get to use a couple % of. So yes, that there are a few perks to living in Australia. It's more socialist. I don't have to pay for that. But problem is it's hard to get money. Period. Unless you burn down. I mean, this is being paid for by burning down. This is the replacement. We've taken 5 telescopes and turned it into this one.
So now you know what to do in 10 years if you want a new telescope.
It's been very painful.
You go from 5 to 1, and the next time.
Yeah, 1 to nothing.
The Brian Schmidt 0.2 meter.
All right. Now you're going to have your discussion on.
Yeah, let's take a game, Brian.